One thing, you don't have to ask my permission anymore for that stuff, right?
True.
It's not.
How's the distance learning stuff going? Are you guys?
I'm literally going insane. I
It's
want to go back
easy.
to school.
Yeah, I mean, it's fun.
easy in my opinion. I wake up at like 8, I get all my work done, then I do absolutely nothing for the rest of the day.
Yeah, easy class.
Billy, you've been doing a good job. You're getting stuff turned in. So
I know. I wanted to do I was trying to do the cold stream thing and like do online classes and all that like last year because I felt like it'd be easier for me, just something I'd like to do. But my dad said no.
Okay.
So
you're getting it done. You're getting it done. All you guys are turning stuff in, so that's good.
And look who's here. Oh.
All right, Arturo's here. Welcome, Arturo.
Yo, it is cold in here, bro.
All right, I'm back.
All right. Started?
Let's do it.
So do me a favor, guys. Does everyone know, I shouldn't take too long today. Like, I'm not thinking we need to have a Google Meet a lot, maybe once a week. And I'm not planning on, like, it has to be an hour for a class. I know different teachers are thinking different things. I do want to touch base with you guys once a week and kind of talk a little bit about maybe some of the more complex items that we're going to be working on. And that's what today will do. If you can do me a favor and mute your microphone for the time being. If you do have a question, unmute it and, of course, speak up. But it just helps so that we're not hearing overlapping audio. Does everyone know how to do that?
Okay.
If you mouse down to the bottom, you should have control over your mics and your video, right?
I got you, Hennings.
All right. Arturo, can you turn on your video? Where's Arturo? There he is.
Yeah, do you want it? Yeah, cool.
I want to see you, Arturo. I got to see you guys.
All right, cool.
So I'm going to go ahead and get started here. The first thing I want to talk about is a little bit about attendance and your grades. You guys are doing really well. In fact, the students at North Tahoe High School are actually doing really well. I think we've all been impressed with people's independence and responsibility. There are a few students that we're really having to track down who haven't gotten in touch with teachers at all. But that's pretty rare. It's pretty far and in between. Most students are saying, hey, I get that. This is a weird situation. It's historic, and we've got some responsibilities to keep our learning up. So on that end, good job. Second thing is, in terms of attendance, right, we're not going to have a Google Meet every day. And but I am going to post every day. There always will be an assignment for you to do. Now, my commitment to you is to make an assignment, in my mind, that's never going to be more than about 40 minutes, and they'll usually be even shorter than that. But what I'm expecting in return is that, yeah, you're going to get on it. You develop a routine like Billy's doing in the morning. You get on it, you get the thing done, and you turn it in. Because what's already happening to teachers and me as well is students are doing it, but they're kind of doing it slow. And what I think should maybe take like a half hour, it just isn't getting done. So that's going to be a problem as we roll forward, because I'm going to be having to document. Students are going to be emailing individually, like, 50 emails about, I have finally turned this in. It was like 3 days ago. That takes an enormous amount of time for teachers to go back and look at stuff. So I appreciate you guys. If I'm going to only give you like no more than 40 minutes of work a night, get that stuff done, get it turned in, get it off your plate, and be, whew, I'm done with physics for the day. Okay. I'm always going to put something in the classroom. So I don't have a form for attendance. You turning the thing in is evidence of your attendance, and it's also progress, gives me an indication of your learning. So that's an important thing. I will put something in Aries almost every day. So at this point for this class, you turned in the check-in at day 1, and I emailed everyone back after the check-in. If you did the check-in, I emailed you, or I also turned in the Penny Lab, which we'll talk a little bit about today, and then the DICE simulation, which was yesterday, and we're going to begin with that then today. You guys have any questions going forward? Feel free to ask or unmute your mic or whatever.
Go for it, Henry.
All right. Let's get going. I'm going to actually pull up, Billy, I'm glad you came this morning because I want to pull up your Dice Lab simulation from yesterday and use it as an example. By and large, people got the idea, but some people kind of missed the details, and we want to learn from those details as we're going to go forward. So I'm going to go ahead. I need to share my screen.
Mr. Hennings, are you ever going to do Google Hangouts? Are you ever going to do Zoom?
Do you guys like? I haven't done Zoom. Do you guys like Zoom better?
I don't even know what it is really.
It's
I know what it is.
It's an app, and I think it does have some good capabilities. I need to experiment. Google Hangouts.
I've heard it's really good.
Google Hangouts, so that's something that's really usually kind of more for small groups or one-on-one. And I definitely encourage you guys in terms if you have questions for like office hours. If you watched my video yesterday, I'm going to have office hours from 3 to 4 Monday through Thursday. So I leave my computer screen up and I hear, like ding, ding, ding. And if you guys have questions, then Google Hangouts is a good way to do that one-on-one, right?
That's cool.
All right. So anyways, I got Billy's document up here. Now I went through this and I highlighted the responses that I was really looking for. I didn't care so much if you did this bonus question, so I didn't evaluate that one. But I do want to evaluate this. So let's just remind ourselves, you were dealing with this piston that had a certain amount of particles in there, and each particle had kinetic energy. So the idea is that each one of these kinetic energy adds to the thermal energy. So that's why we said up here that there should be about 110 joules of thermal energy in the system, right? Because each one has 10 joules and there's 11 of them. So 11 times 10 is 110. So then what I had you do is I had you randomly or spontaneously change those directions. We started off with a 73% efficient engine, and we randomly then changed the directions. And what everyone reported to me in this first analysis question was that after these changes, the efficiency went down. And remember, that was one of the ways that we could say, or we could talk about the second law of thermodynamics. As entropy increases, efficiency goes down. But the other questions are important for moving forward. To ask this, if we assume that when an atom hits the wall, it slows down, its kinetic energy is lowered, where did the rest of the kinetic energy go? And Billy answered correctly. And some people did answer this one incorrectly. The energy is transferred into the wall of the piston, and then ultimately, the energy of the atoms in the piston are transferred to the surrounding air of the engine. So we're losing energy through this mechanism. Every time an atom hits one of these walls, it's transferring some of that energy and heating the wall up. And then because the wall is surrounded by coolant or by air, it's heating the coolant and it's heating the air up. So every collision that doesn't hit the piston is a way for us to lose energy, right? To lose thermal energy to the environment. And that's another way to say the second law of thermodynamics. You must always exhaust heat to the environment, right? The last one then, and Billy got this one correct too, is what happens to the temperature inside the piston? Well, if the particles are slowing down with every collision, the temperature inside is getting cooler and the temperature outside is getting warmer. And that's what Billy answered here. The temperature in the piston lowered, the temperature outside is increased. Now the final one was, hey, did you intend for this to happen? None of you set forth thinking, I want to lower the system's efficiency. I want to have an efficiency less than 73%. But that's what happened to everyone. And that's because there are so many more ways to be disordered, to have these particles moving in all sorts of directions, than to be moving in the ordered state, which is all to the right. There's only one way to be ordered in that case. So, and a lot of people did really well up until this point, but these are the questions then that I wanted to say moving forward. I'm going to go ahead and come back and stop sharing the screen. All right, so at this point, I'm going to go into what we're working on next. Are there any questions?
Did I get the last question wrong or right? The bonus one? I think I put like 1 in 4,096 chance.
Freddie, I'll have to let me go back and look. I'll let you know, okay? Because to be honest, I was doing so much last night, I didn't look at everyone's bonus question.
Okay.
Okay, but I will let you know if you're interested. All right. All right. So at this point, guys, you might want to get a piece of paper out and make a sketch with me, because you're going to see a diagram of what's called a heat engine on some of our problems. So why don't you take a moment and get yourself situated so that you can draw some stuff with me. And this shouldn't take too long, and then we'll be done. I'll let you go.
Hey Wiley, you trying to let me borrow a pencil?
Nah. I might. I'll give you this Apple Pencil though.
Oh, for sure, for sure.
All right, guys, we ready to go?
Yeah.
Yeah.
All right. So the first thing, what we're going to be analyzing here in the next few minutes and for the next few days on your own is something called a heat engine. And the word heat engine makes you think like, you know, like a car engine or something mechanical. And those are definitely examples of heat engines. But there's anything that uses energy to do work, to do physical work, and then exhausts some energy to the environment is technically a heat engine. So animals, human beings are also heat engines. We take in energy in the form of chemical potential, where we eat, we breathe, and the process of metabolism combines the food calories with oxygen. And then we're able to use some of that energy released in that chemical reaction to do work, right? To breathe, to beat our heart, to move, to flex our muscles. But we also know in a group of crowded people or in a room, like at a party or a concert, man, it gets really hot in there. So humans are not just using the energy from their food and oxygen to do work. They're wasting or they're exhausting a lot of energy to the environment. And we know that's the same like in a car or a motorcycle engine. When that thing's running, it gets hot. So a lot of that energy that comes in from gasoline and oxygen, a lot of it, some of it is used to do work, to move the car forward or to move the motorcycle forward. But we also know from being around a working engine, it gets hot. So a lot of that energy is wasted or lost to the environment as well. So anything that takes in energy, uses some of that energy to do work, and then loses some of the energy to the environment is classified as a heat engine. The planet Earth itself is a heat engine. You know, what's moving in planet Earth? Be like ocean currents and atmospheric currents. Our weather is driven by this process. So the input of energy is from the sun. Some of that energy moves and pushes air and ocean currents around. And then some of that energy, again, is lost or radiated out into space. And that's one of the concerns with climate change is if we trap more energy near the surface of the Earth, there's more energy to move the atmosphere, to move the oceans, so we could get more violent or more energetic storms, we think, with climate change. Anyways, we're going to talk about, in the broad sense of the matter, what is a heat engine. So the diagram is really simple. At the top here, we're going to have something which we're going to call the hot reservoir. And that's where the energy comes from. So for a human being, you know, it would be like food and oxygen into our mouths. For a car, it's the fuel pump taking oxygen and fuel into the engine. For the planet Earth, it's the sun. It's the amount of sunlight in joules that are hitting the Earth. So the hot reservoir is our source of energy. Q sub H is the variable that we use. Q is for heat. H is for hot. Right? So some of that energy comes into the system. When we design an engine, we want to use some of that energy to do work. So in our diagram, work is kind of off to the right here. So 100 joules of energy come in, maybe 70 joules of work. Maybe we get 70 joules of work out. And then the first law is also at play, which is the law of conservation. So that means then that some energy has to be lost to the environment, to the colder surroundings, right? And this is the cold reservoir, and that's QC, Q sub C. So are there any questions? Guys, you want to unmute your mic? You have any questions about what you're looking at? I'll go over the math here in a moment. No questions? All right. What do we need to be able to solve here is we need to be able to solve real basic problems. And let's talk about what the basic definition of efficiency is. Well, and the things that we've been imagining, if we had all of our molecules moving in the right direction, we were 100% efficient. And what that meant was, like in the problem you just did with the dice lab, if there was 110 total joules of energy, so I'll do it down here, EFF. If the total energy in the system was 110 joules of thermal energy, and all of them were moving to the right and they pushed the piston and did 110 joules of work, that efficiency, the ratio is 1. If I express it as a percentage, that's 100% efficient. Right? And what we're saying now is that can't happen. There are so many more ways for those molecules or atoms to be disorganized and move in different directions that the efficiency will always be less than 100%, just based on statistics. This is like winning the lottery, right? It's way more than winning the lottery. It's just not going to happen, right? It can, but it's not going to. So that's important that you know how to calculate efficiency. The total energy in minus the work divided by the total energy in. So let's do it real quick. Let's say we have a problem, and we'll make the numbers pretty simple. There are 100 joules of energy into the system. And then let's say this. 60 joules of energy are used to do work. My question for you is, if you understand this simple idea, how much energy did we have to lose to the environment then in this situation? If someone can unmute their microphone and tell me.
40.
40. That's exactly right. That's the law of conservation of energy. If 100 goes in, we have to account for it. 60 we use to do work. So that means then we must have exhausted or lost 40 joules of energy to the cold environment. So now we can do some efficiency calculations, right? What is the efficiency of the system? Well, I'm just going to use this. The work I got out was 60 joules.
Mr. Hennings, I think we're missing a bit of your screen. We can't see the 60.
Can you see now?
A little.
I think it's because you're on a phone.
You can still see it.
So follow along, Arturo. You can
Got
put
it.
it on your Chromebook or something later to see the whole thing.
Got it.
Look into videos.
Oh, you know what? Yeah.
All right. So 60.
You could do both.
The energy right was 100 joules. So the efficiency, the ratio was 0.6. If I express it as a percentage, it would be 60%. Right? So pretty simple idea, right? We're going to always end up usually having some efficiency less than 100%, just because it's impossible to get all of those molecules, all of those atoms working together so that they all turn all of their energy into usable work, right? So then the other problem then, the other equation that we need to know is, what about this? Let me change it. And if you've got this problem down, then you're where you need to be. You're going to have a slam dunk and an easy time on today's assignment. So I'm going to erase the problems.
Good.
All right. Let's do this one. 200 joules of energy come into the system, right, from the hot reservoir, but we're going to lose 150 joules of energy to the environment or to the cold reservoir. How much energy did we use for work then?
50.
That's it, right? Has to be. We got to account for that 200. We lose 150 by heating up the environment, right? If it's, you know, at a dance party or a club, it's the temperature goes up. It's the surrounding air around an engine. Then we only used 50 joules to do work. So the efficiency for this, all right, I'm still going to take 50 over 200. The efficiency for this engine would be 25%. Only 25% of the energy of the joules we're putting in are used to do work, right? And then what Wiley did, I think it was Wiley, right, who was telling me 50, was using this equation, right? Then the work has to simply be the difference between the energy into the system and the energy lost by the system. Okay. Do you guys have any questions on that idea?
This seems really easy. Does it get harder?
Well, it will once we kind of tie in the idea of the probabilities of things. But for right now, no. While it should seem easy, I'm not trying to trick you. It's not overly complex.
Sick.
All right. So then what do I want you to be able to do individually? I'm going to go to our classroom here. And hold on. Present my screen. So up here, I've posted your assignment for today. It says heat engine efficiency problems. It's just problems like what we just discussed. So I'll click on that thing. The instructions are it's just a Google form. So you'll notice, right, when I click on this, here's the pictures of what we just drew. Here's 4 heat engines. The first thing I want you to do is I want you to calculate the efficiencies of the heat engines, right? So down here, just type in how you're getting the efficiencies. Show me your work, though. Show me the ratio of work to energy in that case. Somehow I reshuffled things. You put your name in here so I can document it. Same thing here. Here's some questions where you're doing something like I just did. Here's a missing value, right? If you understand the conservation of energy law, that's a piece of cake. I also want you to calculate the efficiency. And then the final one, there's something wrong with this heat engine, and I want you to tell me what you think is wrong with that heat engine. Okay? And then you'll turn that in. Right?
Is that all?
Are there any questions, guys?
How are you, Mr. Hennings?
I'm doing good. How are you guys?
Do you like my son?
I'm trying to see it. What I see on my screen is a little bit different than what you're seeing, Justin.
This is red.
Bill,
Are we gonna wait? Can you hear me?
Yes.
Damn it.
Are we gonna be in the recorded version of this?
Yes.
Like, how does that work?
Post a Google Classroom.
Well, I'm gonna post. I'll post the recorded version to the Google Classroom. It's basically just going to show you what was on my screen, right, or what you were watching. It's videoing the entire meet, so you'll see what's on there.
That's kind
All
of
right.
kind of sick.
I had a question for you, but I forgot it. It was one of those big brain ones.
Big brain.
Freddie, either email it to me or let's do a Google Hangout at like 3 o'clock today, if you remember.
All right, I'll email you if I do.
Okay. Are there any other questions, guys?
Cool. So just that heat engine problem?
Just the heat engine problems on that Google form, yeah. And then just so you know, I assign something like I just assigned this one day. I wake up real early the next morning. So tomorrow morning, I'm going to get up and check that. And then that's when I document your attendance and how you're learning. So I'm never going to check at a specific time during the day, but by the next morning is when I'm checking for that. Okay.
Cool.
All right, guys. That's all I have for you. Unless you have questions for me, you guys are on your own. You can go start getting to work or do whatever needs to be done.
Cool.
Hell
All right, then. I'll see you later, Mr. Hennings.
All right, guys. Stay
Later,
well.
Hennings.
See you, Hennings.
Bye-bye.
Do we need to hear the bell first?
No, you go. You guys lining up by the door? Are you lining up by your doors right now?
Yeah.
Well, you guys could go. You don't need a bell.
All right, I'll see you later.
Bye.
Shit, easy as hell.
How was that shit? Actually, very bad. One of the niggas was using a knife. Shit's really easy, bro.